All right. Now let's, as we've had this diversion into software and Python and Java and statistics, let's go back and remind ourselves of the physics scenarios and revisit the data analysis. So let's actually do this data, information, knowledge, wisdom pipeline. As we just discussed in the previous lesson, each event is a vector of sensor measurements, such as the signals of the charged particle in an ionized chamber, or the energy deposed when a photon bangs into a bunch of lead or something. Those are called calorimeters. Or the light in a Cherenkov counter, which measures the type of the particle, because the light produced when you go through a so-called Cherenkov counter depends on the mass of the particle for a given momentum. And so it's a signature. As you know the momentum from how much the particle bends in the magnetic field, Cherenkov counters tell you the mass, which allows you to label these things as pions or kaons or what have you. And then because another type of particle is actually weakly interacting particles and leptons and things like that, which are signified by the fact that they do not interact. And so that they just actually pass through chunks of matter. And of course, neutrinos are also in that category. All right, so that's raw data. It's just flying at you from the apparatus, that giant thing. Now we have data, which you clean up by calibrating the information. You get the best possible measured data, and you still have effectively a vector of measurements. Now we want information, which is to convert those original measurements into a specification, not in terms of signals in Cherenkov counters or calorimeters, but in terms of a bunch of baryons, mesons, and leptons and photons. And that takes say, what happens when the particles go through the chambers and ionize, and you detect the ionization. You convert that into a direction and the measure and a bend, which the bend then gets converted into a momentum. So you actually then end up with a list of particles. So this is still a random variable because but it's no longer ionized chamber measurements. Is actually number of pions and properties of pions, etc. And so that's your information. Then your knowledge is gotten by just compiling all sorts of information, by taking all these events and looking at calculating things for each event and forming histograms. That's knowledge. Then you see bumps in the histogram and you will get wisdom, which we didn't put on the slide for some reason. Maybe we thought it was too much enough to get to knowledge. But wisdom is the actual final result of all of that. And the wisdom is the field agreeing the Higgs boson existed, which comes from a complicated set of, you take lots of different knowledges, the different histograms, put them all together, show they're consistent, and can be interpreted as a Higgs boson. So here's a little more detail on the raw data from the ATLAS experiment. Remember, ATLAS and CMS were two major experiments. So we get 25 megabytes of data per event. Most of that data is zero, so it reduces to 1.6 megabytes with compression. And you have about a petabyte of raw data produced every second. Well, that's a little too much. But remember, actually, these protons, we have one proton here, another proton here, they're just passing by each other, and 40 million of them every second, and some of them collide. So, and in fact, a lot of them collide, and you actually have to take all these collisions and extract what you want, which is those collisions which might be interesting. It's not so difficult to decide what's interesting because most particles, when two protons collide, most things just shoot off in the direction of the protons. Only when you produce a heavy particle like a Higgs, it will actually tend to send out information so-called transverse to the protons in a totally different direction. And you use that as one of the triggers of something being important. And So we have these different triggers. Some of them are done on hardware, the actual raw hardware of the apparatus instrument triggers. And the second is you just take this raw data and run it through a giant cluster to select events of interest. So after all of this, around every second we have a few hundred events. And that's hundreds of megabytes of disk space per second. And that's petabytes per year. So that's the raw data. And again, we have the information and the knowledge, which you sort of discussed. The information is this. This is, remember, the raw data effectively comes from CERN. In the previous slide, I pointed out the raw data gets converted to data through calibration. Those calibrations are done by people who deeply understand the experiment and the instrument. I know that an instrument is huge. People seem to think you should keep everything about the experiments. That's not realistic. Only the original experimentalists can possibly understand that apparatus. And so you're going to clean everything up and record for later posterity the cleaned up version of this analysis, because nobody can remember why the particular instrument behaved in the way it did on a particular day, depending on the way the beams are tuned and all sorts of complicated things. And so it is unrealistic to expect you go back to the raw data, except time after time. So when I did an experiment, we once messed it up and had to go back to the raw data after 6 months. That was a catastrophe. Made everybody really unhappy. We just messed up a calibration. Normally, you try not to mess up a calibration and convert that raw data into data. Calibration, of course, needs actually looking at lots of events to try to make certain everything is consistent and that they're not things normalized wrong and things like that. As the offline event construction, which is actually done around the world on this Large Hadron Collider grid, whatever it is, 1/3 of a million cores, and that is using so-called grid computing. Grid computing, this is probably the greatest success of grid computing, the discovery of the Higgs boson. And grids are very suitable for this because you actually want to get the data around the world, because we have these, what was it, 183 organizations in one of those experiments. And so we want to involve all those organizations and their compute power and their understanding. So the event reconstruction is actually done in a distributed fashion, harnessing this infrastructure and knowledge and intellectual digger. So then we get this knowledge where people actually write. There's a famous program called Root, which you use, which reads in the data. You calculate a bunch of information on potential Higgs particles or whatever you happen to be looking at. That's done by physicists who have deep understanding of what a Higgs might look like. And that then gives you histograms which are presented in papers and draw positive or negative conclusions about various effects. So that's what we are. That's specialized a little for the ATLAS experiment. We're basically the same for all those experiments.